Hello, in this particular lecture we are going to discuss about the liquid phase techniques for thin film depositions onto the substrate itself. So, first we have to know that what is the liquid phase techniques actually. The growth of inorganic thin films from liquid phase by chemical reactions is accomplished primarily by electrochemical and the chemical deposition process. So, simply we are having some kind of solvents, we are dipping our substrate into that solvent inside the solvent, then there is some kind of chemical reactions is taking place in between the substrate and to the solvent, and they are forming some new materials, and that new materials forming a coating onto the substrate itself. So, requires considerably less equipment and is potentially less expensive. Easy coating for the large surface area, only we have to check it out that our substrate should be fully immersed into the solvent itself. By using this method, it is possible to form inorganic films homogeneously on various kinds of substrates which are immersed only in the aqueous solutions of a reactant. So, this is also one kind of considerations. So, here simply you can see that we are taking some kind of substrate, then we are having that beaker, then when we are dipping into the solvent is a mixture of copper sulphate with ammonia and with the thiourea. Then it is releasing some kind of copper ions and then the sulfur ions. This copper and sulfur slowly depositing onto the substrate itself, and they are forming the copper sulphide. So, this is the overall diagram that how we are forming the copper sulphide onto the substrate material. So, next we are going to discuss about that why we are using these techniques, what are the advantages of these particular techniques. As we remember that in our last several lectures we have discussed about some kind of vapor mechanism, some kind of thermal mechanisms. So, here we are doing this kind of for the liquid mechanisms or maybe that liquid phase mechanisms. So, these techniques has considerable advantages as compared to other conventional methods such as thermal oxidations, chemical vapor depositions and the sputtering techniques. In particular, these conventional methods require high reaction temperatures of up to several hundred degrees Celsius, whereas liquid phase can be performed at room temperature with low production costs and the environmental impacts. Here we need the suitable solvent and we need that substrate, simply we have to dip into that. The experimental cost is also very less, there is no need of any expensive equipment, and this one also requires the less space and also it can be easily done, and the costing of the solvent is also very less. Sometimes yeah, of course for some special cases maybe it will be expensive, but not up to that much level than other methods. So, the lower operating temperature for depositions do not influence device characteristics and wearing reliability because of decreased thermal stress, and thus it is full on multi-level interconnection interlayer dielectrics. So, here is the examples. So, we are having that quartz tube, it is surrounded by the furnace, then we are having the solvent and we are having the substrate. So, simply by rotating this one we are putting this substrate into the solvent, then chemical reactions is taking place by which we are forming the layer on the substrate itself, and the below one is the FESM and the AFM images, that how we are you making that water induced zinc oxide thin films onto the substrate itself. So, now we are going to discuss this liquid deposition methods into more details. So, here we can see that there are totally 8 methods or maybe that 8 techniques whatever we can apply for this liquid phase techniques. So, first one is called the sealer methods, then electroplating, electrolless-plating, electrophoretic depositions, liquid phase epitaxy, Langmuir-Blodgett, chemical bath depositions and the immersion platings. So, there are total 8 numbers of modification techniques are available for this particular purpose. So, first one by one we will go into the details. So, first we are going to discuss about the sealer methods, SILAR sealer methods. The sealer totally stands like successive ionic layer adsorptions and the reactions. So, sealer is the short form of this sentence. Then it is mainly based on the adsorptions and reactions of the ions from the solutions and rinsing between every immersion with double distilled water to avoid homogeneous precipitations in the solutions. So, here from this particular line we can understand that we are following several steps in these particular reactions. First we have to dip it, then we have to take it out, then we have to clean it, then we have to dip it into the next solvent. So, by this way we can do the coatings of this particular process. So, first we are taking the first precursor solutions. So, simply we are doing the adsorption process, then we are taking it out. So, some precursor molecules is attached with that substrate itself, then we are putting into the water. So, we are rinsing it, then we are putting into some reaction chamber where this solvent is reacting with the first precursor materials, and then again we are deleting or maybe that rinsing it into some water, and then we are getting the first layer of film on substrate. So, simply first we are initially doing the adsorption process, then we are it is followed by the rinsing process. So, by this way we are doing the coatings onto the substrate itself. So, what are the methods? So, this is the very nice examples that growth of the copper oxide nanostructures thin films by using the sealer methods. So, simply first we are taking the adsorptions of the tetramine copper 2 ion onto the substrate itself. Then simply we are removing the ammonia, because when you are dissolving into some water molecules or maybe that water liquid water. So, simply that ammonia it is removing it, then we are decompositions of the copper hydroxide once again, then again we are removal of loosely bounded copper oxide, and then finally we are get the copper oxide nanostructures onto the substrate itself. So, by these methods, one is called the absorption methods and then it is called the rinsing methods. By applying these methods, then again the reaction methods. So, by applying these techniques we are doing the modification, surface modifications of our substrate. Next one is the electroplating techniques. It is not the newer one, it is the oldest methods. Still we are using these kind of methods for our normal samples, because it can be easily done and it is also the less expensive methods and it can easily controllable. So, what are the basic principles? A metallic coating is electrodeposited on the cathode on an electrolyte cell consisting of a positive electrode which is known as the anode and a negative electrode is known as the cathode, and an electrolyte solutions containing the metal ions through the which electric current flows. So, from this particular figure you can understand that we are taking the anode, we are taking the cathode, then we are taking some kind of liquid which is nothing but the known as the electrolytic solutions. So, here we have to keep our substrate onto the cathode part, and whatever the materials we are going to deposit onto our substrate, we have to keep that material into the anode part. Then we have to make certain kind of potential difference in between the cathode and anode, so that these anode materials will release the ion and then that metal ions will transfer and it will deposit onto our cathode materials, that means onto our substrate itself. By this techniques we can do the modifications. So, that is why here we are using certain kind of electrical energy. So, that is why it is known as the electroplating techniques. So, here the important variables in electroplating techniques are current efficiency, current density, current distributions, then pH of that particular solutions, temperature, agitations and the solution combinations, compositions. So, these all are the different input variables for these electroplating techniques which can determine the efficiency for this particular purpose. Here right hand side is the figure already whatever I have discussed. So, this is the schematic representations of electroplating techniques. Next we are going to discuss about the advantages and disadvantages of these particular techniques. So, main advantage, this can be done to protect against corrosions or to improve the appearance of an object. What are the disadvantages? The process is costly and time consuming. Pollution potential, electroplating solutions need to be disposed of safely after use, because it is reacting, it is one kind of solutions, maybe sometimes it can be toxic or maybe some kind of it can be maybe the strong acid. So, after finishing the experiment we have to take care of these waste materials, otherwise this can create some kind of pollutions to the environment itself. Use of electroplating techniques, it is widely used in industries such as automobile, airplanes, electronics, toys, etc. to protect metal objects from the corrosions or rust. So, simply we are doing some kind of stable material coating onto that substrate, so that that stable material can't react with some rain or maybe some moisture or maybe some other chemicals, so that it can give a protections onto our substrate material. To give metal objects a better appearance and attraction, such as jewelry, some kind of mementos, some kind of gifts, some kind of trophies, medals are coated with gold, silver, brass and the rhodium by these particular techniques. So, here we are doing the silver plating onto the cups or maybe the mementos. This is the before picture and this is the after picture. We are doing it for some kind of jewelry, we are using it some kind of medals, mementos and all these kind of techniques. Next we are going to discuss about the electroless-plating. So, now in our last lecture we are discussing about the electroplating techniques, where we are applying the current or maybe that voltage, but here this is known as the electroless-plating. So, from the name itself, here you can understand that here we are not going to use any kind of current or maybe any kind of voltage. So, simple autocatalytic or electroless-plating is a selective deposition plating process in which metal ions are reduced to a metallic coatings by a reducing agent in solutions itself. Plating takes place only on suitable catalytic surface, which includes substrates of the same metal being plated and therefore sometimes called as autocatalysis. So, whatever the materials we are going to take, maybe sometimes the substrate of the same materials or maybe some other materials, and not only that, here we are not going to use any kind of current or voltage. So, that is why it is known as the electroless-plating, and it is the purely chemical reaction based techniques. So, from this particular figure we are going to tell you that how we are doing maybe how we are following this kind of techniques. So, first we are having that support, on top of that we are putting some kind of primary metals, primary materials maybe anything that is platinum, palladium, copper, ruthenium or maybe the silver, etc. Then we are putting some kind of reducing agent on the top of that, like HCHO, H2PO2 or maybe N2H4. So, we are putting, then we are putting then we are creating that ions on that top of that primary metals, then we are introducing the secondary metals like silver, gold, copper, then Re, etc., and then it is reacting with the A materials and they are forming a layer onto the top of the A material. So, either we can do it by the autocatalytic methods or maybe the catalytic methods. So, in the autocatalytic methods already I have discussed that, which includes substrates of the same metal being plated and therefore sometimes called the autocatalysis. So, the same material we are applying onto that, and for the catalytic method maybe we can use the different metal also. So, what are the advantages? Generally selective pattern depositions can be done, no need of external current sources, as already I have discussed. Disadvantages: slow deposition rates, because this is the purely chemical based reactions, it depends upon the solvent, it depends upon the solvent quantity, it depends upon that material which we are going to coat, and then limited to a few metals and the some alloys. This is not means its applications is not the versatile. Then we are going to discuss about the comparison between the electroplating and the electroless techniques. So, these are the techniques actually. For the electroplating, external current source we are using, non-catalytic process, suitable only for conducting materials, because we are giving the potential difference in between the anode and cathode. So, both the materials should be electrical conductive. Difficult for hollow parts, thickness may vary. For the electroless-plating, no external current source we are using, it is a catalytic process, suitable for conducting and insulating materials, okay for hollow parts and blind holes, constant thickness. So, these all are the thickness that whatever we are achieving by the electrolytic process and the electrolysis process. So, this is the in the grey color it is showing the base metals, and green one it is showing the deposition of the material. From this particular figure you can get that for the electrolytic reactions we are not getting the homogeneous thickness onto the substrate itself, but for the electrolysis techniques we are getting the homogeneous thickness for our substrate material. Next we are going to discuss about the electrophoretic depositions. In the short form we are calling it as a EPD process. What the process tells? Similar to electroplating coating, electrophoretic deposition utilizes electrically charged particles moving between two electrodes, an anode and cathode, immersed in a liquid media. The same thing over here. So, here we are using on some kind of charged particles, over there we are using the fluid. Fluid is nothing but some kind of electrolytic materials. Then we are applying the charge ions, that charge ions is depositing onto the cathode itself. Then we here also we are using some kind of voltage or maybe the current in between the cathode and anode. In contrast to conductive electrolytes used in electroplating, the fluids of electrophoretic dispersions are dielectric. So, here we are taking some kind of dielectric medium. Electroplating coatings are built from metallic ions converted into atoms when discharged at the cathodes, where in electrophoretic process the coating is formed by a deposition of relatively large powder particles which may be polymeric, ceramic or metallic. These all are the advantage for this electrophoretic deposition process. So, what are the advantages? So, applicable to any powdered solid sample that forms a stable dispersions, simple experiment setup or no vacuum generally we are using, fast processing, high yield means the output is more or maybe in large, better surface coverage, control of deposition thickness, single step processing, possibilities to scale up for the large area applications. So, there is certain kind of major drawbacks also. So, what are those? So, it cannot use water as the liquid medium because the application of a voltage of water causes the evolution of hydrogen and oxygen gases at the electrodes, which could adversely affect the quantity of the deposits. Yes, of course, because when inside the water we will apply some kind of potential difference, it will generate the hydrogen and oxygen gas which will stuck onto the cathode and anode materials and slower the reaction rates. So, there are some few examples whatever we are using by applying this process. So, composite graphene platinum electrocatalytic electrodes prepared by electrophoretic depositions. So, here we are having the ITO coated glass substrates, we are having the platinum nanoparticles and graphene sheet, simply they are mixing together and then they are forming that graphene platinum composite electrode on the glass substrate itself, and below also the deposition of the graphene by the EPD methods. So, here also we are taking the graphene oxide suspensions and then we are putting the EPO, then we are air drying into the room temperature and there we are doing a graphene coating onto the substrate itself by this electrophoretic deposition techniques. Next we are going to discuss about the immersion plating. So, immersion plating is nothing but it is also one kind of depositions of a metallic coating on a substrate by chemical replacement from a solutions of salt of the coating metals. The substrate metal reduces the atoms of the metal in solutions on itself by reducing the atoms from their ionic state in solutions. Generally a less noble, more electronegative metal displays any metal that is more noble from the solutions. This occurs according to the electromotive force series. So, copper is normally more noble, less readily reactive than tin. So, here the simple is that we are having a base foil with a plus plated copper. So, simply we are taking this one into some tin solvent itself, so that copper ion by the galvanic displacement, simply an exchange of copper with tin atoms, no reducing agent is required. So, simply these copper ions is replaced by the tin atoms. So, like or maybe the tin ions. So, by this way we are doing a coating on the tins onto our substrate materials. So, immersion tin plating on copper conductors in a printed circuit board, generally we are doing like this. So, what are the advantages? It is very simple methods, low capital investment. Disadvantages, limited thickness of depositions can be possible by these techniques. Next one is called the chemical bath deposition process, in short form it is known as the CBD process. So, the chemical bath deposition involves two steps, one is called the nucleations, another one is called the particle growth. It is based on the formations of the solid phase from a solutions, allow to easily control the growth factors, film thickness, deposition rate and quality of crystallites by varying the solution pH, temperature and bath concentrations. CBD is one of the solution phase methods useful for the preparation of compound semiconductors from the aqueous solutions. So, what are the advantages? It does not require high voltage equipment, works at room temperature, thus it is less expensive. Disadvantages, wastage of solutions after every deposition and time consuming process, because you have to allow that material for fully reactions, and also the deposition rate is very slow. Then we are going to discuss about the ultrasonic chemical bath depositions. Only the thing is that here we are using some ultrasonic vibrations by which we can do the coatings onto our substrate itself. So, it is similar to that of CBD, the only difference is the occurrence of ultrasonic waves in the bath solutions. A sonicator is the required equipment for depositing film via UCBD. The probe of sonicator and a substrate has to be dipped in a beaker containing bath solutions for the ultrasonications. An ultrasound pass through the bath solutions, the formation of and implosive collapse of bubbles occurs, this is called the acoustic cavitations. During ultrasonic cavitations, very high temperatures about 5000 Kelvin, pressure of about 1800 atmospheric pressures are reached, followed by release of large amount of energy due to collapse of micro bubbles. It is less time taking process than the CBD, not only that it is more efficient than the CBD process. Next we are going to discuss about the Langmuir-Blodgett. It is also one kind of techniques. The famous scientist is known as the Irving Langmuir and the Catherine B. Blodgett. They have invented these methods. So, just keeping their names, we have given the name of this particular techniques is called the Langmuir-Blodgett techniques. It contains one or more monolayers of an organic material deposited from the surface of a liquid onto a solid by immersing the solid substrate into the liquid form. The monolayers are assembled vertically and usually composed of amphiphilic molecules with a hydrophilic head and a hydrophobic tail, examples the fatty acids. These films are named after Irving Langmuir and Catherine B. Blodgett, who invented these techniques. So, that is why we are calling it as a Langmuir-Blodgett film or maybe that Langmuir-Blodgett techniques. So, here is the schematic diagrams of the Langmuir-Blodgett setups. So, we are having the substrate, we are having that barrier, we are having the scale, and here we are having that bath in where we are keeping our monolayer materials. So, simply first instance we are dipping our substrate into that layer itself. So, generally we are doing it by the isothermal compression methods. So, simply we are dipping the film, then first we are doing the extraction process, then we are immersing process, and like this way we are doing the coatings onto our substrate materials. Main advantage, control of molecular level around 20 angstrom. Disadvantages, slow to fabricate, thick film frying time required after each layer, mechanical and chemical stability is very poor, required the clean room. So, these all are the disadvantages for these particular techniques. So, there are three deposition schemes commonly used to transfer Langmuir film onto solid substrate to form Langmuir-Blodgett film. First one is called the X type depositions, then Y type depositions and the Z type depositions. So, from this particular graph we can see that first we are doing the collapsing, then surface pressure we are keeping around 50 for first phases, then for the second it is 20, then for the ground liquid like phases it is almost varies in between 0 to 10, and the substrate is looking like this. So, here it is a graph in between the surface pressure oblique area per molecule isotherm showing different phase of monolayer at air water interfaces. So, this one is called the X type of films, Y type of films and Z type of films, where we are seeing the different types of deposition process of monolayer films on the solid substrate itself. So, here the how the attachment is taking place. So, by these methods we can see, and we can see that how the film formations is taking place onto the substrate itself. Next is called the liquid phase epitaxial methods. So, epitaxy refers to the deposition of a crystalline over layer on a crystalline substrate. So, it is a layer by layer techniques. The term epitaxy comes from the Greek roots, epi means above and taxis means deposition in order manner. So, one top of another. So, just layer by layer we are doing this kind of modifications. So, epitaxial growth. So, generally we are having that initial substrate, then epitaxial growth is taking place and epi layer is forming onto the substrate itself. There are two types of epitaxy layer generally it can form. One is called the homoepitaxy, another one is called the heteroepitaxy. When the thin crystal layer lattice is the same as that of the substrate, silicon film on the silicon substrate, that means whatever the base metal we are going to use, the coating material is the same. So, that is why it is called the homoepitaxy, and heteroepitaxy is only the vice versa of the homoepitaxy. That means here substrate materials and the coating materials is opposite or maybe the different. So, generally that gallium arsenic film on the silicon substrate. Atoms molecules arriving to the substrate surface may undergo absorption of the surface mitigations and dissociations, incorporations into the crystal lattice and the thermal desorptions. These all are the depend on the substrate temperature. So, by these methods we can do the liquid phase epitaxy onto the substrate itself. Now, there are several types of epitaxy techniques. First one is called the vapor phase epitaxy, molecular beam epitaxy, MBE method, CVD, trimethyl aluminum to deposit onto the aluminum. So, chemical vapor deposition methods. Then we are having that liquid phase epitaxy, LPE methods, solid phase epitaxy, recrystallization of amorphous materials like polysilane. Then techniques, LPE, what is the strength? Simply high purity, less expensive, weakness, inflexible and non uniformity. When you are talking about the HVPE, hybrid vapor phase epitaxy, so it is strength is well developed, large scale process, reactor control difficult, hazardous sources. When you are talking about the MBE, molecular beam epitaxy, so strength is simple, process uniform, as arsenic oblique phosphorus alloy, difficult, expensive, low throughput. When you are talking about the chemical vapor depositions, most flexible, large scale productions, high purity, selective in situ monitoring, expensive sources, hazardous precursors. So, these all are the advantage and disadvantage for different techniques. Now, this is called the process of liquid phase epitaxy film, whatever we are going to discuss. So, it involves the growth of epitaxial layer on crystalline substrate by direct precipitation from the liquid phase itself. A substrate is brought into contact with the saturated solution of the film material at an appropriate temperature. The substrate is then cooled at a suitable rate, which thereby lead to growth of the films. Typical deposition rate for monocrystalline films range from 0.1 to 1 micrometer per minute. So, simply I am keeping my substrate onto the solution itself, then after that we are picking it up. So, slowly the deposition is taking place onto the substrate itself by any kind of chemical reactions. So, here the principal mechanisms of the LP, liquid phase epitaxy, is looks like this. So, first we can do the orientation control, we can do it into the different orientation, so that we can form the different crystal structure onto the substrate itself. So, here we are having several liquid solutions and it is closing it by the graphite, then we are having that substrate and then we are doing the coating onto the substrate itself. So, this is the simple type of liquid phase epitaxy. So, first initially we are having the substrate, then we are putting into the different solvent and then the thin film growing is taking place. Main factors influencing the quality and properties of epitaxial layers: initial equilibrium temperature and cooling rate of the melt, volume ratio of the melt and contact area between the substrate surface and the melt, nature of the solvent and solute and the substrate surface conditions. What are the advantages? Less expensive and higher deposition rates, excellent control of stoichiometry. There are certain kind of disadvantages also. Morphology, that means crystal orientation control is very difficult and surface quality often poor. So, now it is the time to summarize our these lectures. So, we can summarize our lectures in this manner, that we have already discussed that several advantages of the liquid phase techniques such as low temperature process, simplicity, inexpensive, coating for large areas. So, these all are the advantages for this particular techniques. It includes various techniques like electroplating, electrophoretic, electroless-plating, immersion plating, chemical bath depositions, Langmuir-Blodgett films and the liquid phase epitaxy. The fabricated thin films have several applications in optical, sensors, electronic circuit and so on. There are numerous applications. So, depends upon the substrate, depends upon the materials, depends upon the conditions, we can choose any kind of liquid phase deposition techniques based on the applications. Thank you.